You know, in web development, there are some ideas we just accept as true. And a big one is that if you're building a serious app, you need a big, serious database that runs on another server. But what if that whole assumption isn't just wrong, but it's actually hiding a massive performance problem in your application? Well, today, we're going to put that idea to the test.
I'm sure you've heard this before, or at least something like it. It's the standard thinking, right? Postgres is the heavy hitter, the go-to for web servers. And SQLite, that's the lightweight option, great for your phone or some simple little desktop app, but it's not really built for the big leagues. Well, we're about to see about that.
All right, let's get right into it. We're setting up a direct head-to-head challenge. In one corner, the network giant Postgres, and in the other, the embedded underdog SQLite. We are going to throw a ridiculously demanding workload at both of them and see which one even stays standing.
So here's the fundamental difference, and this is really the key to this whole story. Postgres is its own thing. It lives on a server, and your app has to talk to it across a network. SQLite, though, is totally different. It's basically a library that runs inside your application. There is no network. And that one little detail changes everything.
And we are not pulling any punches with this test. We've got a huge table, a billion rows. We're going to hammer it with a ton of simultaneous requests. And here's the important part. We're mimicking real-world traffic. You know how a tiny number of accounts are always the busiest? Think of a few major companies on a payment platform. They create almost all the traffic, which means tons of requests are trying to hit the same few rows at the same time. It's the ultimate stress test.
Okay, so let's see how our champion, Postgres, does under pressure. We're going to start in a perfect world, a setup you would pretty much never use in real life, but it gives us a good baseline.
With the app and the database on the exact same computer, so there's zero network delay, Postgres puts up a really solid number, 13,756 transactions per second. That's a respectable start, but again, this isn't how things work in the real world.
So what happens when we add just a little bit of reality? We're not talking about going across the country here. We're talking about the tiny, tiny delay between two servers sitting in the same room. Just 5 milliseconds of travel time. And boom, there it is. Just that tiny little 5 millisecond delay, and our performance has completely cratered. It's fallen by over 90%. We went from almost 14,000 transactions a second down to just 1,200. That tiny network hop has become a massive traffic jam.
Let's make it even more realistic. We'll bump the latency to 10 milliseconds, still super fast, and we'll turn on the highest level of data safety to make sure every transaction is perfect, which you'd absolutely need for anything important. And just like that, our performance gets cut in half. Again, we're down to a measly 660 transactions per second.
And this is the real kicker. What if each transaction needs to do just one more little thing, like one extra check before it saves? That's one more round trip over the network, and our performance just completely implodes. We are now crawling at 348 transactions per second. We've lost over 97% of our original speed. What in the world is going on here?
The thing is, the problem isn't that Postgres is slow. It's not. And it's not that our server is running out of juice. The answer lies in a fundamental rule of computing that puts a hard speed limit on any system. It's a concept called Amdahl's law. And what it basically says is that your system as a whole can only ever be as fast as its slowest part. You could have a supercomputer for a processor, but if it spends all its time waiting for something slow, then the whole system is slow. It doesn't matter how fast the other parts are.
And in our setup, that slow part is the network. For every single transaction, the database locks a piece of data, sends a message to the app, and then just waits. It waits for the app to think, and then it waits for the answer to travel back across the network. The database itself is blazing fast, but it's spending almost no time working and all its time waiting. The network has become this unbreakable speed limit.
So this is where SQLite comes in. What happens when you use a design where that bottleneck, the network, just isn't there?
Well, because SQLite is running right inside the application, there's no network, no waiting. And the result? A staggering 44,096 transactions per second, right out of the gate. That's more than 3 times faster than Postgres' best case, pie-in-the-sky scenario. But believe it or not, we're just getting started.
Okay, this is where it gets really, really cool. Something that people usually call a limitation of SQLite, that only one process can write data at a time, can be turned into this incredible superpower. Because only one thing can write,
we can cleverly group thousands of little jobs together into one giant, super efficient batch. And we can do this completely safely, using a feature called a save point. Think of it like this. You start one giant transaction, like a huge shipping container. Then, each individual user's work goes into its own little box inside that container. If one little box has a problem, you just toss that one box out. You don't have to throw away the whole container. This gives us the incredible speed of batching, but with the rock-solid safety of individual transactions.
And when we apply this technique, the results are just mind-blowing. We're now clocking in at over 121,000 transactions per second. I mean, think about that. We went from just a few hundred on the network database to over 100,000 on the embedded one. It's not even close.
But what about a more normal workload? With a lot of reading data, not just writing it. Let's say it's 75% reads. Even then, SQLite with its batching trick still crushes it, handling over 102,000 transactions per second. As you can see on the chart, the performance is just in a completely different universe. So, after that grueling test, let's just lay it all out. Let's put the final numbers side by side to see the clear winner of this battle.
Yeah, this final scorecard pretty much says it all. The moment you add even a tiny bit of real-world network delay, the traditional client-server performance just falls off a cliff. By completely getting rid of that network trip, the embedded database starts with a huge advantage and then uses clever tricks like batching to launch its performance into the stratosphere.
So what's the big takeaway here? Should everyone just drop Postgres and start using SQLite for everything? No, not at all. That's not the point.
The real lesson is about architecture. This was never a story about Postgres being bad or SQLite being good. It's a huge reminder that the most dramatic speed improvements don't come from tweaking code for hours. They come from taking a step back, looking at your whole system, and getting rid of the slowest part entirely. And that brings us to the final question, the one you should be asking about your own projects. The next time you hit a performance wall, before you start thinking about more servers and more complexity, ask yourself, what's my real bottleneck? Because as we just saw, sometimes the most powerful solution is actually the simplest one, hiding in plain sight.